So we know everything there is to know about ionic bonding, right? We know that there's a positive ion, that's the electron donor. There's a negative ion, that's the electron acceptor. And electrons will be transferred with the goal of having all atoms achieve a full outer shell, usually an octet. So now I want to jump ahead a little bit. This is experience 5, so we're looking at page like 95-ish in the book. And I want to look at how to write names and formulas for ionic compounds. So while the ionic concept is fresh in our head, let's talk about writing the formulas. And to be honest with you, writing these ionic formulas is a skill that must be mastered. This doesn't go away when this unit is done. We're going to deal with ionic compounds all year long. And so it is something that we have to feel really confident with, that we can write ionic formulas forwards, backwards, upside down in our sleep. This is going to be great. So first of all, there are 4 different types of ions. 3 of them are what we call monatomic. Monatomic just means a single atom. Monoatomic, one atom. So there are some ions that just exist as one atom. There are a lot of ions that exist as a one atom. Here are the 3 types of monatomic ions. So if you're looking at groups 1 or 2, the alkali metals or the alkaline earth metals, these are all positive. They're positive ions. The alkali metals are always +1, and the alkaline earth metals are always +2. Okay, so these guys will be named with just their element name, and then we add the word ion at the end. So all we do is say sodium ion versus sodium atom. And anytime you see the term ion, then it means the charged version. So I have to think, okay, ion, sodium. What is sodium going to do to achieve a stable octet? Oh yes, sodium's got 1 valence electron. It's going to lose 1. If I'm down 1 electron, then I'm overall +1. I've got an extra proton, right? And so anytime you see the word ion, it means the charged version. Atom means the neutral version. So it's really easy to write the name of an ion in groups 1 or 2. All you do is put the word ion at the end, right? Now the negatives, like the nitrogen family, oxygen family, the halogens, the negative ions aren't bad either. We're just going to take the name of the element and change the ending to IDE. So for example, like chlorine turns to chloride, or oxygen turns to oxide, phosphorus turns to phosphide. And for a while, I'm not going to be super picky if you spell it goofy. Do your best. The ending should be IDE. And if you say something like phosphoride, fine, I get it. I know what you mean. And we're just going to be using these ions all year long. So eventually you'll get used to nitrogen, nitride, phosphorus, phosphide, oxide, sulfide, selenide, or telluride. And then all the halogens turn into halides. Fluoride, chloride, bromide, and iodide. So we change the ending to IDE. So if you ever see an ion that ends in IDE, then that's referring to a negative, an anion. And then we have to include the charge. Now the only group that's a little bit funky are the transition metals. So the transition metals are in the middle, right? And we said earlier that transition means a change. And so the problem with these ions is that the number of valence electrons can change. And sometimes there's more than one way of getting a stable electron configuration. That results in different charges. And so that's what makes the transition metals a little stinky, in that they can have different forms and different charges. So if you say, yeah, I'm looking for the iron ion, which one if I like go in the lab and I'm looking for compounds with iron ions, there's two different versions. Iron has a +2 charge, or it commonly has a +3 charge. Which one do you want? You can't just say, go get me a compound with iron ions. Do you want the +2 version or the +3 version? They have different properties in the lab. And same thing happens with copper. Copper is commonly either +1 or +2. And by the way, I think we mentioned earlier too that when you see just the plus, it just means +1. Same thing with the minus. Sometimes they don't put in the 1. Obviously you can, and often I do. But like if you just see a minus or a plus, it means -1 or +1. We also mentioned that it's okay to say like -2 or 2-. Same thing. Either's fine. Totally fine whether you say like +2 or 2+. I totally get what you're meaning. All right, so I mean, even some of these transition metals like manganese, for example. Manganese can have like 4 different charges, and vanadium can have about 4 or 5 different charges. And so we have to find a way then of saying what charge we're referring to. And that'll be shown with a Roman numeral. So you're going to see something like this: iron Roman numeral 2 or iron Roman numeral 3. Same thing for copper. You would see copper Roman numeral 1 or copper Roman numeral 2. And that Roman numeral means the charge. And these are all metals, they're transition metals. And so the charge will always be positive. Metals are always positive, they'll lose electrons. Non-metals are negative, they tend to gain electrons. Okay, so look for the Roman numeral when it's a transition metal, and it's not a big deal. We read it as like copper 1 or copper 2. And that 2 or 1, the Roman numeral, is just telling you the positive charge on the ion. But it's really important, because if you just say, go get some copper ions, I don't know which one you want. And again, they have different properties in the lab. Okay, so here's 3 main groups of the periodic table. We've got the first 2 groups, the alkaline earth metals. Those are easy. We just say ion if it's charged. The transition metals will have a Roman numeral. And I should also mention this, that not only will you see transition metals with the Roman numerals, but you'll also see them with tin and lead. Like down in here would be tin and lead. And technically they're not transition metals, but they can have multiple charges. So transition metals, tin and lead, will always have that Roman numeral to tell you the charge. And then finally, when you get over to the negatives, just change the ending to IDE, and that represents then a negatively charged ion. Now the 4th category of ions are called polyatomic. Polyatomic just means many atoms. An ion is like, no, ion means charged. So polyatomic ions look like little formulas, but they're not neutral. They have a charge. Now here it says that they're covalently bonded, and we'll deal with that later. But I mean, you could see something like NO2. Looks like a cute little formula, NO2. And we have things like CO2. We're familiar with that. But NO2 just isn't neutral. If you want to bond nitrogen and 2 oxygen, you can do it. But you're going to need 1 more electron so that the nitrogen and both oxygens can get a full octet. That's what we mean by something like NO2 minus, or -1, or 1 . It's the nitrite ion. Looks like a cute little formula. It's just not neutral. And again, it's not neutral because if you want to bond nitrogen and 2 oxygen and give everybody a full octet, you're going to need to gain 1 more electron. You'll be short by 1 electron, so you got to gain 1 more. Then everybody gets a full outer shell. Here then is a list of a whole bunch of them. Now you might want to find a sticky note or a bookmark or just a random piece of paper to put in your book at this point. Because for any test or quiz where you would need it, you can access this chart of polyatomic ions. And they're super common. We're going to use them all year long. And you don't have to memorize them. You just have to know how to use them and when to use them. But that's where this chart's going to come in really handy. And so all year long, you'll want to have quick reference to obviously the periodic table at the back of the book, but then also this chart of polyatomic ions. So bookmark it in some way, fold in the corner or whatever. You can use this on any test or quiz where you would need it. And so all of these little guys look like tiny little formulas. NH4, adorable. Yeah, the problem is if you want to bond nitrogen with 4 hydrogen, you're going to have 1 extra electron. So you'd need to get rid of it. So something like NH4 then ends up having a charge of +1 or 1 plus. In the end, we want a compound to be neutral. So if I need a couple more electrons, I'm going to have to note that with a negative charge. And if I have a couple extra, I'm going to have to note that as a positive charge. Now these guys are grouped according to their charge. There's a whole bunch that are charged -1, -2, -3, and then there's little baby ammonium. That's a positive one. Again, you don't have to memorize any of these. They do kind of give me a little hint with the endings. Polyatomic ions will either end in ITE or ATE. Now the difference just depends on how many oxygen. Often the ATE is the most common form. It's like we're going to use tons of nitrate. All year long we're going to use nitrate. 1 less oxygen is the ITE ending. So for example, nitrate and nitrite are at the top of this chart. Nitrate is the most common. It's NO3 -1. If you have 1 less oxygen, it goes nitrite. Now, if you ever see NO2, you can just look it up on this chart. You don't have to memorize them, but there is a little bit of a naming scheme here. And the same thing happens with like hydrogen sulfate and hydrogen sulfite, or chlorate and chlorite. The ATE is the most common version, but if you go 1 less oxygen, the ending turns to ITE. Same thing happens with sulfate and sulfite, phosphate and phosphite. The ATE is PO4, 3-. 1 less oxygen is PO3, 3-. Charge stays the same. It's just 1 less oxygen. And so keep this chart handy. These are ions that can then make compounds. I mean, if I have something like ammonium NH4 +1, well, +1 means that it wants to give away 1 electron. So then somebody needs to take that 1 electron, and it would form then an ionic bond. So these are little formulas that need to bond with something to either gain a few electrons or lose a few. You do not need to memorize them, but have them handy. And so in number 25 here, it says, how are the chlorate and chlorite ions different from each other? How are they similar to sulfate and sulfite? And so if I look them up on that chart, chlorate is ClO3 -1 or 1-. I'll write 1-. I'll do it the same way as in the chart. 1-. And chlorite, ClO2, 1- or -1. Sulfate is SO4, 2 minus or minus 2. And sulfite would be SO3, 2 minus or minus 2. And so the first question says, how are the chlorate and chlorite ions different from each other? Well, these guys are differing by 1 oxygen. So the ITE ending means 1 less oxygen. All right, so I'm just down 1 less oxygen. ATE, most common, most stable in a lot of cases. ITE, 1 less oxygen. Same charge though. How are they similar to the sulfate and sulfite ions? Well, gosh, I would say the same thing, right? That the ITE always means 1 less oxygen. But maybe we'll make a little note too that the charge stays the same. So between chlorate and chlorite, they're both 1 minus or minus 1. Sulfate and sulfite, same charge. The ITE ending just means 1 less oxygen.